All right, this is preliminary part 2 of the proof of the mean value theorem. I'm going to explain a little bit about the motivation behind it. So here's the setup. First, I believe you're familiar with the statement, but we're going to write it here that we have, I don't know what happened, is A, point A and AB, and we have a condition, usual condition on continuity and differentiability, and then we have these 2 points. And there is this secant line that's passing through, and the actual function actually looks something like this. And the claim is that there is C inside this AB, not on that boundary, and that's also a key part, such that the slope of the secant line FB minus FA divided by B minus A is realized as a slope of a tangent line, and somewhere that place, that C that we're talking about. So I have to adjust a little bit. So here I'm explaining with a little bit of different things. So there are several points, and here's one point where there's this slope is almost parallel to that. So that's what this means, slope of the secant line, and there's another point, things like that. So there's several points, but we have to kind of choose one point that and go for it, rather than knowing that there are many possibilities like that and vaguely just looking for any C without having this picture of this, how this proof is done. It would be kind of tricky. So we got to aim something that we can easily describe, and the idea is one that is further away from that secant line, and this one, it seems like a furthest away from the secant line. So we're going to write down not just any of them that we're looking for that C, and we're looking for the special one. Then our search without having any detail and can be actually done. So here it is. So the furthest away one, and I'm going to write down that tangent line, or the function for that line is going to be m0. That m0, I forgot to write this one m0 here. The slope of the secant line is m0, and that line is, of course, is going to be m0 x plus k1, which is y-intercept, though that line that is further away from that tangent line. This one has a property that because it's further away, every line is at the part of the graph of f of x is below that line, just like that, some concavity condition. So we have this condition in here. This gives us an idea where one line we're looking for is line with this property. I was wrong. Actually, it has to be greater than. The line is greater than the function. Everything, all the functions below that line. If you happen to be looking at that one, you can imagine there are different shapes. For example, like this. There's a tangent line. Maybe graph is something like this, and then you're not going to have anything further up way. So we have to also look for one down there, m0x plus k, so different line that has a property that everything, the function, is always above. Every part of the graph is above that line. So there's one inequality description of the line we're looking for, not any of the random line. And we hope that this will capture that property. This is a motivation. So I'm going to do very simple algebraic manipulation on that one. If the first one becomes m0 minus f of x greater than negative k1, m0x minus f of x, which is in this case is less than negative k2. Once you do this simple algebraic thing, what happens is that this m0x minus f of x is like a function, and everything is known. m0 is predetermined, x is the main variable. This k1 and k2 is something what we're looking for. But if you look at this function, and if you look at the relationship between these two things, this is happening for all x in that interval. So this looks like a maximum minimum. Not of the function f of x, but of this function that we're looking at in here. And this is the motivation. This function in here we're looking at. And if we find the maximum minimum of this one, maybe we're going to capture this property. So this is explanation towards the very beginning of the setup of the proof of the mean value theorem. So proof begins in the next part. Once we look at this function, and proof is fairly simple. I was trying to explain the setup and with this motivation. So proof actually begins here, and the proof begins with the setup. That's this part we just discussed. Don't have to be the part of the proof, just explaining the setup. So let this function g of x be m0, which is the slope of a secant line, x plus minus in here, f of x. So that's the function. And we're looking for a maximum minimum, and here's where it kicks in, the extreme value theorem kicks in. Often a student will just ignore that part and let there be a maximum minimum. Here it's very general discussion. We don't have a picture of this graph of f of x, so when we are asserting something, and you have to be careful. So what this extreme value theorem is asserting is because polynomial function is assumed to be differentiable and continuous. Because of the extreme value theorem, we have a maximum minimum. G of x is trapped in this value, capital M and little capital M, where M and M are extremum values. Maximum minimum, namely. So there we use this important extreme value. The next part is these two cases, and it falls out really quickly. There's two cases. The first one is the case this maximum or minimum, it doesn't matter which one, is achieved in that interval a to b. That's what we're assuming. And next case, we have to take care of what if neither the maximum minimum is achieved within this interval a to b. This case is really plausible. This happens, so that means g of c achieves this little m or this big M, which is the maximum. So I fix that part. For c being inside this a comma b. Okay. And here's this important theorem again, something called, we called in our class, this local extremum point theorem. Local extremum point theorem says if the point we're looking at, g of c, is happened to be a local extremum point, and if it is differentiable, then it implies that g prime of c is 0. Okay, so because we're inside, we have left hand out, left hand right, and so that we have this kind of local extremum point to make sense. So because we're inside that interval a to b, so we have this condition. So we're going to just simply write down the meaning of g prime of c being 0. That's the point. So it's not an arbitrary c. It was the maximum minimum, absolute maximum minimum we're using to pull out this g prime c condition. So 0 is equal to g prime of c, and g of x is this formula right there. M0 is when you differentiate is 1. When you differentiate that one is f prime of c, that is 0. So if you separate this two part, m0 is equal to f prime of c. That m0, on the left-hand side, is actually the slope of the secant line. I'm going to write down f of b. So like that, I just wrote down what m0 is more explicitly, and that equals f prime of c. When does it happen? It happens when this one of this line is hitting this maximum or minimum, and it is happening inside the interval a to b. And then this f prime of c being equal to that falls really quickly. It's not the maximum minimum of f of x, but maximum minimum of this function here fell naturally from this consideration. Now we'll be back here and have to take care of one case. That what if this m or m, neither of this absolute maximum minimum, is not achieved in a and b, inside an a and b. Then it has to be in only one case, because we do have absolute maximum minimum achieved. That's the extreme value theorem. So if it is not the case, then it has to be endpoints is either a and b. So I'm going to write it in this way. The other case is the following. So I wrote it like this. If capital M or M is not, neither of them is achieved inside, then both maximum and minimum must be achieved in the endpoints. So GA is M and GB is capital M, or the other way around, something like this. So we have a little bit of specific information here about G of X. So we'll see what happens if I plug in G of A and G of B and try to simplify as much as I can. So first I'm going to write down G of A. So I use the formula M0 minus X and I plug it in F of X equals A. So here we're going to use this M0, that's what M0 is, and plug it in here. And you can see a lot of terms are similar, so you have to simplify. So if I replace this M0 with that expression, it looks like this. And we have to take the common denominator and put it into a single fraction, and then numerator will be a lot simpler than this. So that's the next step. Okay, so I multiply b minus a and both the numerator and denominator here and put it into a single fraction. And a is distributed in here and there. So I want you to look at this part. To see some cancellation, I see b times f of a is not cancelled, but a times f of a here, a times f of a is a positive, and there is a negative a times f of a. So these terms and that one cancel out. So after these two terms cancel out, we have two terms left, and this is as simple as it gets. I guess. So that's it, and we're going to go to G of B. We do the same thing, and you plug in x equals b everywhere. So if you do b, and we have these terms, and then we're going to simplify just like we did it before. I wrote it down, but it's running out of space, so I'm going to move it a little bit. So we're looking at this one. This FB is multiply b minus a and b minus a is all in the numerator now. Then what we have, I see some cancellation. This b together with FB is cancelled with b times FB. So without that, we have two terms left. So these two terms left is, if you put this positive symbol one out first, it's AF of B and BF of A. And here we are noticing that what we have down there and up there is exactly the same. A of B, BFA, AFB, and BFA. So we can see easily from that algebraic calculation that G of A and G of B are exactly the same. We did that because of this condition. The maximum minimum is supposed to be equal to G of A and G of B, and we have a little bit more explicit expression than just G of A, G of B. So we came back here and calculated this to see what happened. And this is what we have discovered. This is a more explicit expression, but G of A equals G of B surprises us because both of them are supposed to be part of the maximum and the minimum. And we're saying this maximum and minimum is equal to each other. So I'm going to write down that inequality that I wrote down at the beginning. By extreme value theorem, we know the existence of maximum value and minimum value, and from there we realize this maximum value and minimum value, they're equal to each other. That forces the function g of x to be a constant function, because smallest number and largest number is the same. What can happen to g of x? It's not really the squeeze theorem. It's a conclusion toward to g of x being this absolute constant like that. And the consequence of that is that because it's always a constant, maximum minimum is everywhere. So it's a contradiction to what we have supposed here. Both m and r not only obtained it here, maybe I wasn't specific enough, it is G of A, and since we oppose real hypothesis here, and both m and r not obtained inside. So that's what I should have written. So I'm going to go ahead and change it. So I fixed it over there. The right negation of the earlier statement, number one, we assume that it's achieved inside. If not, we have to write none of those, not achieved within that one. So therefore, it has to be outside the boundary. So G of A and G of E must be that. So after all the calculation, we realize that G of X is actually a constant function, and constant function forces that the G of this whole thing is now constant. C is equal to the minimum and equal to the maximum. And because it's a constant, some G of C is going to be in the maximum and a minimum. And this is a contradiction. We said that in the hypothesis earlier there, maximum and minimum are not achieved in an A comma B. So in this case, cannot happen. That's what we have proved. You don't have to differentiate anything. We just prove that if we suppose this possibility, you run into a contradiction. So this doesn't really happen. Sum of minimum maximum is taking place within that interval a to b. So the only meaningful case, and we have to consider, is this one, but in the proof you have to explain why this case number 2 is ruled out. So I think that concludes the proof of mean value theorem. So here's a typical symbol of the end of the mean value theorem, but let me emphasize this again, the importance of this mean value theorem and the structure. There is this kind of sitting at the bottom of the chain of reasoning extreme value theorem. And independently, we prove this local extremum point theorem. If it is local extremum, the derivative is 0. And using this together, these two things, and we establish the mean value theorem, which is kind of intuitively true when you're looking at the picture, but we established that without actually relying on the picture is very algebraic and calculation. And we discussed in class the consequence of the mean value theorem. All the graph test theorem, we actually proved one of them, but all of them is kind of relying on this important theorem. Increasing and decreasing related to positive and negative property of a first derivative, concave up and down, and those things is a graph theorem. As a second one, and I named it as a theorem like this, the theorem of near uniqueness of antiderivative. Antiderivative is not unique, but its structure is well understood, and because of that, lots of physics problems in differential equation has a very unique solution. So that unique solution is an important theoretical foundation so that we can rely on mathematics to predict something, because mathematics says, and proving that that is the only mathematically possible solution to a certain problem. So it's an important step toward to understand something called the uniqueness of a differential and differential equation. So in that importance of whole discussion, and sitting behind it is mean value theorem, and is rooted in the chain of mathematical reasoning. This extreme value theorem and local extremum point theorem is behind it. Thanks.